Hello, in this video we're going to talk about simplifying square roots. Now you might recall in the last section we took a look at evaluating square roots. For example, if we had the square root of 25, we knew that that was equal to 5. Or if we had the square root of 64, we know that that equals 8. But what happens if we are looking at the square root of, say, 24? Well, that's not a perfect square. We've kind of talked about that already. And we've also talked about the fact that we can find an approximate value because it would give us an irrational value. But today what we want to look at is how can we make this value smaller so that we can actually work with smaller square roots when we get into adding, subtracting, multiplying, and dividing square roots. So in order to do that, we need to take a look at a very important little rule called the product rule. The product rule states the following. It says that if you have the square root of A times the square root of B, it's equal to a single square root where you multiply A times B underneath. Now, you also want to keep in mind with this particular rule that this is going to be true only if A is greater than 0 and if B is greater than 0. Remember, we talked about the fact that we're only going to look at the square roots of positive values, so this little part of the product rule tells us we are only working with real numbers. So let's see what this would look like with an example. If I were to look at the square root of 9 times the square root of 4, what this rule tells me is that I can combine that 9 and 4 and make it the square root of 36. And notice that I can take the square root of 36 and that is equal to 6. Now I could have also taken the square root of 9 and said the square root of 9 is 3 times the square root of 4, which is 2, and said 3 times 2 is equal to 6. So there's two ways of doing it, but the way the rule applies is it's going to help us with numbers like the square root of 24 that we're looking at up here. So let's take a look at the square root of 24 and see what ways we could write this using the product rule. So let's factor the square root of 24. So if I'm looking at the square root of 24, I could say it's the square root of 1 times the square root of 24. I could say that it is the square root of 2 times the square root of 12. And I could say it's, let's see, other factors would be the square root of 3 times the square root of 8. And I could say it's the square root of 4 times the square root of 6. Now all of these would give me the square root of 24 if I apply the product rule. But what I'm really looking at now is using that product rule in reverse. Most often we're going to be trying to find two factors of a number that will break us down into two radicals, and the one being a perfect square. So of these four ways, the most useful way to simplify the square root of 24 would be this last factoring that we came up with. You'll notice that it's the only one that has a perfect square in it. So if I look at the square root of 4 times the square root of 6, I can say that that is equivalent to 2 times the square root of 6. And typically we take the times out and we just write it as 2 square root of 6. This is the simplified form of the square root of 24. Okay, so keep in mind that the key that you want to remember is that anytime you are simplifying, you want to look for a perfect square factor of the number in the, that the radicand is. So let's look at some more examples. Let's start with the square root of 120. Here is a little bit larger number we might not be used to working with. So how do we figure out what might divide it evenly? Well, think about your perfect squares. One really isn't going to help me a lot because it doesn't break the number down and make it smaller. So the first one that I always consider is the first perfect square I have is 4. Does 4 divide 120? Well, actually in this case it does. So I can rewrite this again using the product rule in reverse. This becomes the square root of 4 times the square root of 30. So when I simplify that, the square root of 4 is 2, and the square root of 30 I'm going to leave as the square root of 30. Now, one thing you should always do when you've simplified a problem is take a look at your answer and ask yourself, can this radicand be simplified any further? Well, let's see. 30 is 3 times 10. Those aren't perfect squares. 5 times 6, nope, those aren't perfect squares. 2 times 15, no, there's nothing that's going to divide that that is a perfect square. So in this case, I know I'm done and I've simplified this as far as it will go. Let's try a couple more. Let's say, for example, I'm looking at the square root of 75. Now again, you might not right away see a perfect square that divides into it. Maybe you do see it already, but let's start with 4. Does 4 divide 75? No. Well, my next perfect square is 9. Does 9 go into 75? Nope. Well, then I have 16. Does 16 go in? Nope. What about 25? Oh yeah, there are 3 quarters and 75 cents. Now I remember 25 does divide 75. So I can rewrite this as the square root of 25 times the square root of 3. Again, the square root of 25 is 5. The square root of 3 I leave as the square root of 3. Now, unlike the previous example, the square root of 3 is a prime number. I can't make that any smaller. So anytime I have a prime number as the radicand, I know that I am done. So there is the square root of 75 simplified. Let's try another one. Let's try the square root of 63. Square root of 63. Now, you might start picking up on some of these numbers a little bit more quickly. Notice 9 divides into 63. So I can rewrite this as the square root of 9 times the square root of 7. Square root of 9 is 3. So I have 3 times the square root of 7. 7 again is prime, so I know this is as far as it will go. Now, it's really nice if you can automatically find the largest perfect square that divides into the number right away, but sometimes that's not easy to do. So let's take a look at an example where I'm going to kind of lead you through a thought process that could occur on this problem. Square root of 48. So square root of 48, I go, oh, look, 4 will divide into it. I've got a perfect square. So I look at the square root of 4 times, well, let's see, 4 goes into 48 12 times, so that's the square root of 12. Square root of 4 is 2, and I get 2 square root of 12. Now I need to look at this 12 and ask myself, is that as simplified as it can get? And you should be saying, no, it's not, because 4 will again divide the 12. So I would need to rewrite the 12. Now notice I already have a 2 here, so don't forget that. So this is going to become 2 times the square root of 4 times the square root of 3. And I can rewrite this as 2 times 2 times the square root of 3. Now I'm leaving the multiplication symbols in here for you to clearly see that this is all multiplication. Since these are both outside of the radical, I can now multiply them together, and this would become 4 times the square root of 3. Now this would happen if I didn't recognize that there is a shorter way of doing this one. If I would have immediately recognized that for the square root of 48, it's actually the square root of 16 times the square root of 3. That would have right away given me the answer of 4 square root of 3. But you may not always recognize the largest square root right away, so being able to go through a couple of steps to get this answer is perfectly fine. Just remember to always ask yourself at the end of a problem, can I simplify further? Now we're going to turn our attention to simplifying some square roots that have variables in them. Now variables actually, I think you'll find, will be a little bit easier to work with than numbers are. So one of the things to remember with simplifying a square root with a variable is that a variable is considered a perfect square if it is raised to an even power. So we can refine our product rule when looking at variables. Basically, when we're looking at the product rule and dealing with a variable, we can say that the square root of a variable raised to the 2n, meaning there's always an even variable or even exponent represented, that will always equal a to the n. Again, you want to keep in mind that a has to be greater than or equal to 0. So let's look at an example applying the rule to it. Suppose that I have, for example, the square root of x to the 6th. According to the product rule, what I would have would be the square root of x to the 2 times 3, which means that this would simplify down to x to the 3rd. Notice that in my example, the 3 is the n. That relates back to the product rule. Another way of thinking about this, and I always find this a little bit easier to work with, is if I am looking at the square root of x to the 6th, I need to have a pair in order to take 1x out. And so I could simplify this by just thinking, what is 6 divided by 2? That's equal to 3, so this becomes x cubed. That's another way that you can work with this rule, and it might help you simplify these types of problems a little bit more quickly. Let's try a couple more. Suppose I have the square root of y to the 14th. Well, again, think about how many pairs of y's do I have? What is 14 divided by 2? Well, it's 7. So this simplifies down to y to the 7th. What about combining a couple? Suppose I have x to the 4th, y to the 10th. Well, now I need to think about these two variables, and I can think about them separately using the product rule from earlier. What is the square root of x to the 4th, and what is the square root of y to the 10th? Well, the square root of x to the 4th, how many pairs of x's do I have? That's going to be x squared. How many pairs of y's do I have? Y to the 5th. Or 4 divided by 2 equals 2, giving me the 2 over here, and 10 divided by 2 is 5, giving me the 5 over there. So if you have an even exponent, it works out very nice and neat. But what happens if you have an odd exponent? Suppose that you have the square root of x to the 7th. Well, we can still use the product rule to simplify this a little bit, in that I'll take out the even ones that I have here. So I could rewrite this as x to the 6th times the square root of x. Again, breaking the x to the 7th into two separate radicals. Now we've already talked about what happens when you have an even one. So I know I'm going to look at pairs. So there's 3 pairs. So this is x cubed. But this little x under the radical doesn't have a partner, so I can't pull an x out of this particular radical, so it remains as the square root of x. So it is possible that you may not be able to pull all of them out. Let's try another one. Suppose I have the square root of y to the 15th. Well, again, that's an odd exponent, so I look at what the even one that is in there. That's going to be y to the 14th, and I'm going to have 1 left over. So now the even one, y to the 14th, how many pairs are there? There are 7, so that's y to the 7th, and then I have a y left under the radical. Now let's try to put all of this together. Let's take a look at a few examples of putting it all together. First one I'd like to look at is one with just variables. Suppose that I had the square root of a to the 21st and b to the 10th. Now notice one is an odd exponent and one is an even exponent. So I'm going to start by separating this out as a to the 20th times the square root of a, again making sure I have an even exponent with my a, and then I can also separate out the b to the 10th and look at that separately. Now a to the 20th, how many pairs are in there? There are 10 of them, so I can pull out 10 a's. I'm left with the square root of a, and then I also have 5 pairs of b's, so this will be b to the 5th. All right, let's rewrite that a little bit just so it looks a little bit nicer. This would become a to the 10th, b to the 5th, times the square root of a. Let's try another one. Suppose we have the square root of 16y cubed. Well, now we have a number and a variable. So again, I'm going to break that apart and look at the number part, and I'm going to look at the variable part. The product rule is very nice to be able to pull these things apart. Now the square root of 16, I already know what that is. That is 4, so I'm going to go ahead and write that down. But again, the square root of y cubed, I need to think about how many pairs there are. Well, there is a y squared and a y there. Again, it's odd. Now y squared is a pair, so I can pull a y out. So I've already got my 4. This becomes 4y, and then I have the lonely little y left under the radical because it doesn't have a partner to get rid of the radical. So we have 4y square root of y there. Let's try one more. Suppose we have the square root of 72x squared. Oops, make sure that radical goes all the way across there. Again, I have a number, so the square root of 72 times the square root of x squared. Now, in this particular case, 72 isn't a perfect square. I wonder what the largest number is that will divide 72 evenly. Now, it might take you a couple of steps to get there, but I happen to know that the square root of 36 times the square root of 2 will give me 72. And then I have my square root of x squared. Well, let's simplify what we can here. The square root of 36 is 6. Then I can't break down the square root of 2. That's just going to stay the square root of 2. And the square root of x squared is x. Now, this presentation is a little awkward as well. We typically will put the square root at the end. So I'm going to rewrite this as 6x times the square root of 2. You'll want to get in the habit of writing it in that format as we start moving on into adding and subtracting. That will really help a lot. Let's do one more example. Suppose I have the square root of 18 x to the 4th y. Now I've got a whole bunch of stuff, but the product rule allows me to pull all of this apart. So I'm going to look at just the number times just the variable x times just the variable y, and I'm going to simplify each piece to start with. The square root of 18, you might be getting a little bit better at this, but it does break down into the square root of 9 times the square root of 2. Now, the square root of x to the 4th, I think I can simplify that. How many pairs are there? There are 2, so I can actually pull out 2 x's. So that becomes x squared. And the square root of y, well, that doesn't get any smaller, so I'm going to have to leave that as the square root of y. Now the square root of 9 also simplifies, so this becomes 3 times the square root of 2 times x squared times the square root of y. Now I talked before about wanting to make sure that anything outside of the radical comes first, so I'm going to take that 3 and that x squared and write it first. But now what do I do with this square root of 2 and this square root of y? Well, at this point, since it's as simplified as it gets, I'm going to recombine it and make it the square root of 2y. So this now is as simplified as it gets.